Hello friends, my name is Derek Carter, and in this video we're going to continue talking about some of the mathematical building blocks of neural networks. So previously we looked at the data structures and data types that are used for a neural network, and those are basically using tensors to represent data and pass that around. So in this video we're going to be looking at the gears of neural networks, okay? So tensor operations. So basically all transformations learned by a neural network or a deep network can be reduced to a handful of tensor operations or tensor functions, okay? So we're talking about here, after the network's been trained, when you give it an input, it's going to transform that input through its layers, through these tensor operations, to get the prediction or the output that it wants to give, okay? So conceptually, what is happening, the most common kind of thing in like a dense layer, the transformation is doing is this, okay? So it takes the inputs and it does a dot product or a matrix multiplication times its weights, right? So it's one of the two parameters we've talked about for the layers of a neural network. Then that dot product is added, so we're doing a matrix vector addition to a vector of biases B. And then we do another transformation on the layer before that is sent as the output, as the input to the next layer in the network. We do some activation function. So, for example, like the rectified linear unit that we talked a little bit about. So it's useful to get an intuition, a geometrical understanding of what these operations do, like these basic ones. What can happen with a dot product, what can happen with addition, what can happen with activation functions like ReLU. So let's start with ReLU, although we will come back to that one later. So ReLU, just for every element in the tensor that you pass it into, it applies this function. ReLU is relatively simple. It's just applying kind of I think of it as a clipping function, right? So any value that's greater than 0, it just returns the original value. And any value that's less than 0, it returns it as 0. Any value that's negative is returned as 0, right? So we can write a naive implementation of this, right? So if we're passed in this implementation from our textbook and in this example notebook, expects that you pass in something that's two-dimensional, right? So it won't work on data, but you know the ReLU can be generalized to any dimensional tensor that you pass in. Right? But in this case, if it's two-dimensional, a naive implementation is just go over every row and column, and for each item in the input tensor X, we just clip it, right? So take the maximum. If it's bigger than 0, we take the value, and if it's less than 0, 0 would be the maximum. We clip it to 0. All right. So that hopefully that makes sense, right? So likewise, we could implement an add, right? So if we wanted to add together two tensors that are of the same shape, so we're expecting two-dimensional things that have the same shape. So in that case, we just go over all the rows and columns and add every item of y to X and return that as the result here. We made a copy of X before we returned it, so we're not modifying the original X when we do this here. Okay? So if you look, we're just showing examples of using our naive implementations here. So we do the naive ReLU. So again, notice this is element-wise. So anything that was negative gets clipped to 0. And then here we show an example of using the implementation of the add tensor transformation that we just did by hand. Right, so you can go through and check this for yourself, but it should add every corresponding element to the randomly generated X and Y here. So X and Y are both shaped 5 rows and 5 columns with that integer values between -5 and 5. Right, so when it adds 3 and 1 for the item at index 0, row 0, column 0 to the 3, it gets a result 4 and so on. So you should get exactly the same results if you use NumPy, right? So the whole purpose of NumPy is to implement these kinds of tensor operations, but do them in highly optimized, high-performance ways, okay? So NumPy and TensorFlow are basically tensor libraries that perform these kinds of tensor operations that we've started talking about, but they they do them using highly optimized libraries like the BLAST library. So they'll be much faster to actually do addition or these other operations than if we do it like in our naive implementation before. So you should get the same result if you do the addition followed by the ReLU of x and y, which we did here. So if you compare that to, I don't know if we did that before, but you would get exactly the same result, but this is highly optimized. So if you compared the time of doing these, so if we have, again, two random arrays of the same size, if we do it with NumPy, where we do the addition and the ReLU activation, it only takes 1/10 of a second. Whereas you'll notice the delay, if we do it with our naive implementations, it takes 100 times longer, over a second, typically, usually. Right? So that's a difference of 2 orders of magnitude. So you would never want to use these naive ones if you're building or trying to train or create neural networks. You want to use an optimized library like TensorFlow or NumPy. In the previous example, I did mention that the addition between the result of the matrix multiplication with the bias values, the bias is really usually a vector in these layers. So, you might have been wondering how, if you looked at that more closely, how can we add a matrix with the vector? They're not of the same shape, right? And our naive first versions didn't do that. So that brings up, normally broadcasting is supported by these sorts of tensor libraries. Like NumPy does this automatically for you. So I'll just go through this quickly. So what it means is that, for example, if I want to do addition between x and y, if we want to do it the way we did it before, we would have to sort of do broadcasting by hand, which is what we're doing here. So originally, y was just a vector, which had the same number of features as the second dimension, the feature column for x here. So if we want to do an add normally in NumPy, we would like to do broadcasting. So every value of y should be added to every row, each of the 10 features of every row of x, so 32 times. So we can do that broadcasting by hand by reshaping y to be two-dimensional with just one row, and then repeating that row 32 times, which is what we did here. But if we wanted to have an implementation of the add that we did before, it's fairly simple. We can accept like a vector instead and broadcast it. So all we're doing, the modification before, is that for every row of x, we're adding in the values in y, right? So we repeat that for every row that happens. So, you should probably review broadcasting if this is unfamiliar to you. So NumPy and TensorFlow will support this natively. So there is restrictions. So for example, it only works if I want to broadcast y onto x, it has to have the last same dimensions, however many dimensions we're broadcasting onto. So here, this will work because y is 32 by 10, and that matches the dimension size of the last dimensions of x that we're going to broadcast the element-wise maximum do here. You'll see, so you might think that it ought to work like this because y has 320 elements, which is the same as the last two dimensions, but it won't do that automatically for you. So to get that to work, you would have to actually reshape this into something that's 32 by 10 dimensions to do it. So the tensor product or dot product is one of the most common and most useful tensor operations. So this is really just another names for matrix multiplication. So if you haven't, so this is, again, I would recommend maybe doing a little bit of a linear algebra review about matrix multiplication. Performing the dot product if you're not familiar with that. So I do have materials for doing a review of linear algebra available for this class. So all that happens with matrix multiplication is if I have two tensors, here x and y are tensors, x is some shape a, b, so they're both two-dimensional, but this does extend to more than 2 dimensions. So if x is shape AB and y is B of C, we can, the matrix multiplication is defined on these, right? As long as the last dimension of the left-hand side is the same as the first dimension of the right-hand side. The result of doing the matrix multiplication will be a resulting array that's of shape AC here. So what happens for matrix multiplication is each corresponding row of X is multiplied by the corresponding element in a column of Y here, right? So basically, the element 0 in the row here is going to be multiplied by the element 0 here. The first element is going to be multiplied by this first element, so on, down to the nth element here will be multiplied by the nth element here. And these have to have the same number of elements, again, because the number of rows, sorry, the number of columns of X here has to match the number of rows for this to be defined, right? So, but then the multiplications are then summed together. So that's why you end up with a single value, which is a scalar value. Right? So, and again, if you do that over arrays or tensors of shape AB and BC, the result will be, resulting tensor will be of shape AC. Okay. So that's what the tensor product looks like. In NumPy, you can use the NP, the dot member function to perform matrix multiplication. So this is defined, for example, in vectors, right? So since these are vectors, you can think of this as an array having 32 rows, and this is an array as having 32 columns, and this is an array of having 32 rows. So basically, each item is multiplied together, and then they're summed up. So that's why when you do a vector-vector dot product, you get a single scalar value result. In Python 3, the at operator was overloaded. I think this works in TensorFlow as well. It works in NumPy. So that also does the dot product. So we should get the same result. So you'll see me use both of these in our example code here for the class. So you can implement the dot product in code relatively easily, right? So here, we're doing this to do the multiplication of 2 vectors. So we're expecting 2 vectors. All we do is multiply each corresponding elements and sum them together. So our naive implementation should get the same result as what NumPy returned, but again, much slower since it's not doing it using optimized code. You can multiply a matrix by a vector. So in that case, you'll get another vector when you do that. So, and that's, so like in this case here, we have a matrix of size 5 by 10 and a vector of size by 10. So the result is kind of like a weighted sum. So we're going to multiply every row by the items in the vector, sum those up. So we'll end up with 5 values. That's the result of doing that dot product between that multiplication of y by each row of x. Right? So you'll see we get 5 results from doing that dot product of x with the vector y. And we could have reused our function here. So instead of doing this, we could have called the naive vector dot product. So we already saw in our slide that the matrix multiplication is defined as long as the shapes have a match. So basically, in code, if we have x and y, as long as the last shape, so here we're assuming 2-dimensional, but again it would work even if it's 10-dimensional. So as long as whatever the last dimension shape is for x is equal to the first dimension shape for y, matrix multiplication is defined. So again, if you have x and y you want to multiply, the last dimension, and they're both 2-dimensional, the last dimension matches the first dimension of y, so the resulting shape would be a 32 by 10 shaped matrix if we do the dot product. So again, you should be able to implement this by hand relatively easily. So we just go through the rows and columns of x and y, multiplying the corresponding item. So actually what we do here, we reuse the naive vector dot function. So we get the row and the column that we want to multiply and sum together. That's what the vector dot would do. It would multiply these corresponding elements, sum them together, and return them. That should be the result that goes at row column, or the resulting z. Okay? So, so these are just some examples. So here, if we have x and y are 3 by 10 and 10 by 2, our resulting matrix would be 3 by 2, and this is the result using our naive version. We should get exactly the same result if we do it using NumPy, using the operator here. And yeah, finally, this is defined for more than 2 dimensions, right? So if I have a 5 by 3 by 8 by 7, I want to take that with the dot product of 7 by 5. The resulting shape is going to be a 5 by 3 by 8 by 5 resulting tensor in this case. So another thing that we often need to do is to be able to reshape tensors. So we often need to do that in order to get them in the right shape to perform the operations like we're discussing here, like a multiplication or addition or something like that. In fact, we already saw an example of that. We actually reshaped the MNIST training data set. So originally when you load it up, you get a 3-dimensional tensor that has 60,000 samples in 28 row by 28 column image is, or pixels, 28 pixels by 28 pixels. So our simple dense layers expect a flat input. So we had to flatten the training and test data before we could use it for using the TensorFlow layers here. So we did that simply by doing a simple reshape. Okay? So if you're not familiar with reshaping, again, I would encourage you to do some review of doing NumPy. So reshaping is a basic fundamental thing that can be done. So the only constraint is that the resulting shape has to match the number of elements, right? So the number of elements in the 6,000 by 784 is the same as the number of elements in the 6,000 by 28 by 28. But if you just multiply all of the values of a shape, that's the total number of elements that you have in that data type. So you can always reshape into something that has the same number of total elements. Okay. So there's a couple of examples of reshaping there. A special case of reshaping, so this is doing more than just reshaping, it's actually rearranging the elements. So the rows become the columns become the rows, right? So we're exchanging rows and columns. So we often have to do the transpose on matrices, again, for some linear algebra operations that we do in this class. So finally, this is kind of probably the most important point of this lecture is we really want you to build up an intuition of what these tensor operations are doing when you do them in like a linear regression or do them in a sequence in multiple layers in like a neural network. So it's good to understand like the geometric interpretation of some of these tensor operations to get a better understanding of what's happening. So for example, let's consider the addition of a vector. So if we have a vector with 2 values a, so this is where a little bit of that confusion between the number of dimensions comes in. So we would call this a 1-dimensional tensor, but you can also interpret this as a point in the 2-dimensional space whenever you have a vector like this. So here, the A has the location 0.51 in 2-dimensional space. Okay? So now consider another point B at 1 and 0.025, and let's say we add them together. Right. So what happens for addition, if you think of one or the other of these as a translation, as a specification of how much we want to translate something. So kind of what's happening for A is we're translating it by 1 unit in the first dimension and by 0.25 units in the second dimension. So A goes from here, gets translated by 1 here and by 0.25 up here. Right. So tensor addition represents the act of translating an object. Okay, without distorting it by some amount, by some certain distance. Okay, so our textbook shows something like this, right? So you can think of doing an addition as applying a vector to a point or a set of points in order to do a translation by some fixed amount. Again, this we can only visualize this in 2 dimensions, but this works in high dimensional space to perform a translation like this. Okay. So So as an example, to do a similar thing to like that image from the textbook, if we have a shape, so we defined a shape here as a set of these 4 points, so some kind of a polygon, what's the technical name for that? Rhombus? So anyway, if we have a shape, if we want to perform a translation, we can do the same thing. So we have our translation factor, and we're just going to add that onto the points of our shape to translate it by 0.2 and 0.3 in our 2 dimensions by our translation factor. So the result of doing that addition on our new shape position is it just translated 0.2 on the x and 0.3 on the y. Moved it from here to here. Every point was translated along that vector. Okay. Okay. So that's one thing that can be done with addition. So multiplication is used for lots of different kinds of transformation. So there's lots of different geometric interpretations that can happen from performing a matrix multiplication on an array of values. Okay, so for example, rotation can be achieved by performing the tensor product of a particular type of matrix. So our textbook shows it like this, right? So if you create a 2-dimensional square matrix, if I want to rotate by theta, so rotate by theta degrees here, if I create a small matrix of that size and do a matrix multiplication times the set of values that I want to rotate, I will get a rotation in my space by that number of degrees. Okay, so here in this example, we're going to create that matrix like we showed in the textbook here, where we want to rotate by 22.5 degrees, or by pi divided by 8 radians. Right? But all we're doing is a matrix multiplication by that matrix times our original shape S to get the new shape. So the result should be that original rhombus or whatever it is rotated by 22.5 degrees positively. Okay. Another thing that matrix multiplication do is perform scaling. Right. So here, if we create a translation matrix, something like this, so for 2 dimensions, we would have a square 2x2 array to do a scaling. So I think it's the first column is going to be, so to interpret this, basically what will happen here is we're not going to translate or scale the first dimension, so it remains the same. So the x dimension is the same, but the y dimension gets scaled by 0.5, so it's half the size, and the negative causes it to be flipped. Okay, so this is still a linear transformation. Every point in the original is translated to a new point in a linear function here. Right, but this causes both a flip and a scaling of the resulting image by doing this matrix multiplication. Right. So again, it's this example from the code where I changed it so that we're going to actually scale to make it 50% bigger on the first dimension. We're going to make it 50% smaller on the second dimension and still flip. We do it this way. Right, so the result of this should be it's flipped. We made it 50% bigger this way, but it's only half the height in the first dimension. Right. So these are both linear transformations, and there's another thing I would encourage you to review from linear algebra. If you don't know exactly what I mean by linear transformation, you might want to review that. So this might not look like a linear transformation, but it is. So, but everything we've talked about so far are linear transformations. So rotation, this kind of scaling, or flipping, or just the translation using addition cause linear transformations here. So a technical term you might see from our textbook is that an affine transformation is just a series of linear transformations. Right? So if I have multiple linear transformations in a series, the result, we call that an affine transformation. So this, if I do a multiplication of the weights times the inputs, so that's doing one kind of a transformation, and then if I do an addition to do like a translation, this is still a linear transformation. Okay? So as an example, a quick example, this one, if we combine those, if I can go back to here, if we can combine those, the multiplication by the addition, I can do a like a rotation and then a translation at the same time. So we rotate the figure and translate it a little bit. Or the same thing here in our example of our code. So I can combine the same scaling that we had before instead of a rotation. So I'll scale it like we did before, and then we'll do an addition in order to do a translation by 0.5 and 0.2. Okay. But these were both linear transformations here. Okay. So the point should be made, if I didn't make it here, this is kind of important, is that a sequence of linear transformation, so an affine transformation, if I do that in multiple layers, I can reduce that to a single transformation. So even if I have 100 layers, if they're all just performing simple linear transformations, I could have an equivalent network that has a single layer that would do all of those at once. All right, so in that case, having multiple layers is not more powerful than just a single layer, as long as you just reduce the sequence of linear transformations to the single linear transformation. So that's where nonlinear transformations come into. So one of the secret sauces of a neural network is you have to have nonlinear functions, transformations in there as part of what the neural network is doing. So the where that mostly happens are the activation functions. Okay, so like the ReLU activation, the last thing that happens after we do the multiplication and the addition of the parameters times the inputs is we put it through a nonlinear activation function. And the result of that is what is output to the next layer. And every layer usually does a sequence of linear transformations and a nonlinear transformation. Okay? So back to our example from the textbook. If we do the same transformation, but then also put it through a nonlinear ReLU, it would look something like this. So again, it looks kind of like it's being clipped here, but really what's happening is every point is translated to a new point, but from the nonlinear activation, it gets translated in a nonlinear way. So these points that are below, that get translated to be below y, get translated all to y equals 0 in the resulting nonlinear transformation. Okay. So again, we can do the same thing with our examples. So we do the same example we did before, but as a final, we use the minimum function. So here we're doing basically the same thing that's done on usual basic dense layers of a neural network. A matrix multiplication, which will do a kind of transformation. An addition will usually do a kind of a translation. And then we do a nonlinear ReLU activation here. So the result is the same that we'd had here, but the ReLU geometrically, it looks like it clips those values to y equals 0. All right. So finally, just to summarize this, so a neural network consists entirely of a chain of tensors, of tensor operations, and it can be useful to build an intuitive understanding of the geometric interpretation of those transformations. So that's what I was trying to do in this lecture here, right? So these can be interpreted as transformations of the input data into a new space or new manifold, right? So so you can interpret what a deep neural network is doing as a very complex sequence of geometric transformations in a high dimensional space implemented via a series of these tensor transformations we talked about, right? So by analogy, you might think of it, if this is our input, hopefully what we can train, what the network can learn to do is uncrumple the paper, right? So if I need to read the data on this paper, if I perform the transformations to unfold it, unwrinkle it, spread it out, then it will be much easier to accomplish the task to read the data that's on the paper there. All right, so that's it for this video. Hope that video was useful for you in building intuition, and I hope that you join me for the next video. See you later.